Alright, we got a minute, so just general reminders, you all make certain you're working through the problem sets. If you haven't started already, fantastic. Stuff's hard, y'all. If you haven't seen it before, it's going to take some time. You may run into some questions that you can't answer on your own, or you may need to look up information through YouTube videos, or work with instructors, like go to my office hours, or the help room, or all that kind of jazz. But the first step to fixing a problem is realizing there is a problem, and so you have to start solving problems for that. That's just how it goes. Alright, so last class, let's just jump right into it. Last class we finished up 1D kinematics. So we reminded ourselves we got this wonderful list of equations, and we spent a lot of time, and so basically remember the way to engage with these equations is when you're solving a problem, write your givens, write what you're solving for, and then you're going to choose an equation that has what you're solving for, and ideally has your givens. Now, if you choose an equation, you're like, this doesn't have everything, I don't have all the other pieces of information, you have a couple options. One, look for a different equation, or two, maybe you don't have all the givens. Maybe you haven't identified all the givens. We talked about some examples. We gave some things. Remember, if something starts at rest, that means its velocity, its initial velocity. If it starts at rest, its initial velocity is 0. If it ends at rest, its final velocity is 0. But during my office hours, thankfully someone came on by. Please visit me, y'all. I don't know why this, again, like if you don't, I'm not offended. But I really love it when you all do come visit me. One, I get to know you. And two, it actually is immensely helpful for me because it gives me a better finger on the pulse in terms of the challenges that may be encountered and what common concerns. Because I can guarantee you, if you have a question, many other people have that same question. So someone came by today and it was awesome because it actually helped me to realize there's a couple useful things. So I'm going to start off with a couple clicker questions because there's a couple concepts that I didn't necessarily make explicit. You'll kind of end up discovering. You may or may not end up discovering them. But they're really useful, specifically for problems in the air. So last class we said if something is in the air, A is negative 9.8. So again, that's one of those that's not going to say it in the problem. You have to know that. You have to know if it's in the air and it's not rocket powered, or, if gravity is the only thing acting on it, A is negative 9.8. There's a couple other ways to actually figure out givens in a problem. And one of those was that, and I did mention this one, if I toss something straight up at its highest point, the velocity is 0. That's another one of those things. It won't tell you that in a problem. That's something that you have to know, that if something gets tossed straight up in the air at its highest point, its final velocity is 0. Here's a couple more things that may be useful for us. Oh, man. I was so optimistic. Wait, how does that even make sense? I have a play button right here and it still wants me to log in. That is so sad. Maybe it's going to work. Fingers crossed. It's gone. Okay, well, you all can see the problem. Oh, it did work. How weird. Okay. You try to be prepared and technology throws a curveball and then the whole program crashes. Okay, I toss the ball upwards. How does the time to the top compare to the time from the top to the bottom? Try it out, y'all, while I reopen the clicker program that just spontaneously crashed on me. I toss the ball upwards. How does the time from my hand to the highest point compare to the time from the top to the bottom? Think about it. You got some time, clearly. I've realized some handy things here. One. Good, I can turn off the display. Goodbye, online people. You can no longer see my password. So think about that, y'all. People in class can no longer see it. So how does the time to the top compare? Yeah, that wasn't going to go well. There we go. And I'll give you all foreshadowing. The next one's going to be how's the velocity at the bottom compared to the velocity at the top. Okay. And we may come back to this once the clicker thing comes up. So I'll give you all the answer now. We'll come back to this. I'll give you the free clicker points. Ostensibly, the clicker program is opening. So, the really cool thing about this when you toss something up in the air and gravity is the only thing affecting it, if I video recorded a ball getting tossed upwards, and I stopped the video at the highest point, and I played that in reverse, it would look like a ball falling. You would actually not be able to tell the difference between a video played in forwards, going up, and a video played in reverse of a ball falling. So all that tells you is this is a symmetrical situation, y'all. Whatever on the way up, it's the exact opposite of a ball on the way down. So what does that mean for my answer here? That means that the time it takes is exactly the same. The time it takes for a ball to go from the highest point to the lowest, from the lowest point to the highest point, is the exact same as the time from the highest point to the lowest point. And that's useful. If you can find the time from the bottom to the top, and you say in my problem, I tell you, hey, find the total time a ball is in the air. I toss it straight up. If you can find the time from the bottom to the top, just multiply by 2, that's the total time. Yeah?
I thought, because in my mind, like, if there's something really hard, but I thought that after it stops on the top,
yeah,
it just fall down with gravity instead of with the force that you throw it.
Sure, so that's going to actually lead us into the next question. So once it leaves my hand is no longer acting on it. And so this is actually going to segue us very nicely. Let's see, is my iClicker very angry? It's already running. Great. Through the power, I'm not going to risk this. I already made that mistake once before. So the next question is going to be if the thing leaves your hand with a certain velocity, how fast does it return to your hand? And we're going to discover that as well. So my apologies, y'all. I fully blame technology for this. Everything was already open. And then it just decided not to be. But hey, this is what happens. Of course it's in progress. All right. Boom. Resume. Here. Hold. Y'all got... So here's the question. Go ahead and spend the 30 seconds answering the one that I just gave you the answer to. Give me all 3 points. Now that everything is totally going to work for me and not crash again. Yeah, what a waste of time. All right. Cool. All right, 30 seconds, because again, you know the answer. Actually, I'm at 20 seconds. Let's just move on with our lives. This is one of the this is a good time to mention as well. If you are streaming this online, one of the bummers is no matter how low I set the delay, there is a delay. So if I set a question for 30 seconds, and the delay is 30 seconds, by the time I open it online, by the time you see it, I've already closed it. There's no getting around that, y'all. 3, 2, 1. I guess the only way around this is the second I send a question, it goes immediately to your thing with no delay. So if you are online and you are at home, just make sure your phone is like right there so you can see when they pop open. Yeah.
So for me, I'm kind of confused because if you have gravity at 9.8, toss it up, wouldn't the gravity be slowing it down on the way up and then speeding it up on the way down?
It will be. So if I toss a ball upwards with some velocity, at the highest point it's not moving. And let's go ahead and jump to the next one, and then we'll kind of unpack the whole problem together a bit more. If I toss it upwards with a velocity of 10 meters per second, what is the velocity when it returns back to my hand? So the key to this is symmetry. And so I'll talk through this one, so this will give me some time. To answer that kind of question, remember, if I record a video, you can test this for yourself. If you record a video of someone tossing something in the air, so if you toss something in the air, heck, record the whole video. If you played it in reverse, it would look identical. It would look completely identical. Because as it's coming up, you're right, it is slowing down, but it's slowing down at the same rate that it's going to speed up with when it comes back down. So the same rate it's slowing down, so say I start at 10 meters per second, at the top it's going to be 0. So whatever slowed it down, it went from 10 meters per second to 0 meters per second. So the answer to this one, I'll give you all 5 more seconds. 5, 4, 3, 2, 1. And this one may have thrown you all off. Vectors matter, direction matters. This is another key point. It's the exact same value, but the other way. So acceleration acts on it at all times. So acceleration is slowing it down to the highest point, and then on the way back down, it's speeding it up, and it will return with the exact same velocity it left my hand with. It's a symmetrical problem, y'all. If you kind of just watch something going in the air, yes, I had to toss it to get it going, but the second it leaves my hand, gravity is the only thing affecting it. And to prove this to you all, try it out. Try the math. At 10 meters per second, we know the final velocity is 0 at the top. Find the time of that. Literally do the math. So this, what I'm teaching you all, can all be proven with this math right here. If you find the final velocity is 0, initial velocity is 10, a is negative 9.8, you can find the time to the highest point. Okay? And then you can kind of do the opposite problem. I dropped something. And you may ask yourself, oh gosh, how do I know that the final velocity is the same? Let's see, do we have another equation we can kind of choose here? We know initial velocity is 0, xf, xi, that doesn't really help us. This equation kind of works. If you flip these, it doesn't change much. So, anyway, you can play around with the numbers, basically model both problems, and it's going to return with the same velocity. Like, the time's going to be the same, the velocity will be the same. Play around with these, kind of prove that to yourself. Watch some videos, but yeah.
What if you were to throw it at above, like at a speed higher than, not a speed, but velocity greater than its terminal velocity?
So we're ignoring air. We're ignoring air here. That's very important. If air is acting on this, everything I just told you is incorrect. Remember, in these problems, air is not acting on it because air makes things much worse. But the reality is, air doesn't affect, if I toss it just a little bit, it doesn't affect it that much. Unless I'm working with a piece of paper, in which case, whew, you know, way different. So, ignoring air. Very important for us to ignore air. Yeah.
So, with no air, there wouldn't be like terminal velocity?
There is no, it would fall faster and faster. And if there is no air, this is the reason why things in space can go really fast. The fastest, I believe, on Earth is like Mach 8. That's 8 times the speed of sound, and they've gotten it like a plane. The things going in orbit are going Mach 30 or something stupid. Faster than that even. That's why when they hit the atmosphere, there's a lot of fire, because now there's air, and then they start slowing down. Yeah, if there was no air, things would get faster and 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 faster until it eventually hit the Earth. Yeah, it's a great question. All right, cool. So let's get into any other questions about this, because again, these are some useful things for you all. All right, so the key takeaways from this little thing I just said here. This is some more given information. If I toss a ball straight up and I say, how long does it take to return back to my hand? And if I say I toss it upwards with a velocity of 10 meters per second, a secret given that you actually know is that the final velocity is negative 10 meters per second. But you have to, again, there's often more than one way to solve it. These kinematics, there's often several ways to solve them. Pick whichever one involves the least math. So, and by recognizing more givens, it gives us more options. Okay? So, important things. Again, play around with this, y'all. And the problem set, I really, really like number 6. Again, during office hours today, what inspired all this was working through 14 and 16 with someone. And those are great problems because they are going to make use of what we just kind of talked about. Those are going to be helpful things for y'all to realize. So, try it out. Investigate it. And yeah, record someone tossing something upwards and play it in reverse and see if it looks any different. All right, so today we're going to get a little bit further in 2D kinematics. Remember, the punchline of 2D kinematics. We're using all the same equations that we did for 1D. X and Y are separate. So when we're going to be solving problems, the name of the game is what you do in X. So the X, Vx, Ax, so the position, left, right. The velocity, left, right. The acceleration, left, right. Should never be mixed with the position, up, down. The velocity, up, down. The acceleration, up, down. Up, down is Y, left, right is X. Those should never be mixed together. The only time you will see those together in the same equation is if you're combining final position in the x and final position in the y, and you are using the Pythagorean's theorem. So we'll do some practice. That is the only time they come together, is at the very end when I say what's the total displacement. I have a vector in the x, vector in the y, combine them together. So we'll practice that today. So yeah, we mentioned that last class. Look, there it is. At the very end of a problem, sure, if I say find the final displacement and you know the x component and you know the y component, that is the only time they come together. In our kinematics equations, they should never be in the same equation. I should never see gravity in the x direction. Okay? So again, this is just a recap of vectors. Nothing really too fancy here, so I'm going to kind of move on to the next thing. So last class we talked about, displacement. It's what we've talked about, but now it's 2 dimensions. So if we want to find the total displacement, we find it in the x, we find it in the y, we do Pythagorean's theorem. So let's make certain we're good at doing Pythagorean's theorem. A bird flies 3 meters east and 4 meters north. What is the bird's net displacement? Here's a nice little never eat soggy waffles. That's the way to remember north, south, east, west. It's convenient because left is kind of subjective depending on which way you're facing. East is always east. West is always west. North is always... So east is always kind of based on this. Where if I said to the right, it could then put in your perspective. So 3 meters east, 4 meters north. I'll give you all till a minute, so 20 more seconds on this, because this isn't anything too fancy. Is the answer A, 7 meters, B, 1 meter, C, negative 1 meter, or D, 5 meters? All right, 5, 4, 3, 2, 1. All right, let's draw a picture, y'all. To the east is to the right, so we're going to draw a vector to the right with a size of 3 meters. We are then going to go up. 4 meters north is upwards. I have made myself a beautiful triangle. The net displacement is right there. And this is actually a very nice, this is the 3, 4, 5 triangle, y'all. Meaning, if you ever have a triangle that has sides 3 and 4, the 5th, it's just a really nice ratio. You can plug that in a calculator for yourself, but great job, great job. We're going to have to do this in problems. At the end of a problem, after working out all the kinematics in the x and all the kinematics in the y, if I say find the net displacement, you got to do vector things. All right, let's see. Is this the problem that I thought I moved to later? Yeah. All right, we are not going to visit this problem right now because it involves velocity. So we're gonna come back to this one. We're going to solve it. But let's go ahead and introduce velocity first. Remind ourselves of that. In fact, this is written here twice. I thought I deleted this one. Goodbye. It's gone. All right, it's going to show up later. 2D velocity. It's the same thing as 1D velocity, but there's an x component and a y component. Same exact thing. Velocity is defined as the derivative of position derivative of position with respect to time, just like it was before. Just now, we have x and y, and both are treated separately. Both are treated separately. The velocity vector is the rate of change of x with respect to t in the x direction, and the rate of change of y with respect to t in the y direction. If you want the net velocity, you will find each of these. You will then do a triangle. Pythagorean's theorem. Again, vectors, vectors, vectors. You always started with it for a reason. It is a necessity that you are good at vectors. If you are not good at vectors, please be practicing on this, because literally the next 3 weeks is vectors galore. It's a requirement to solve, x and y are independent. They're vectors. This is what you got to do. There is no shortcuts. All right. Same thing. You want to find the net velocity. It's a triangle. Already said that. All right. So let's see. There you go. This is a good one. Let's see if this is what I wanted it to be. Yes, I'm fine with this. A bird flies for a total time of 2 seconds. A total time. During this time, It's going 3 meters east and 4 meters north. What is the bird's, we're going to say net velocity in this. Okay, do I like this problem? I don't think I like this problem. No, I really don't like this problem. Okay, this problem is not good. Go ahead, just pick answer B, and then we're just going to move on. This problem's not great because what I should have done is I should have given you the time that it travels east, and I should have given you the time it travels north. This problem is assuming, so when it says it makes it 3 meters east and makes it 4 meters north, it's kind of confusing because it almost makes you think it goes to the right and then it goes this way. But this problem is saying that the bird travels this way, and it's not necessarily clear in the way I've worded it, so that's why I'm kind of going through this. So this problem is saying that I do drive that 5 meters that we just calculated. It's not going 3 meters east and then 4 meters north. That is not what's happening. It's going in a straight line, but it's just not worded great. But long story short, velocity is distance divided by time. That is the definition of velocity. So if we travel 5 meters in 2 seconds, we get our answer. So anywho, I really, really hope you picked the right answer. Let's see how people did. Nope. All right. You got 5 seconds to pick I can't even click it, but it's that one. You got 3, 2, 1. Again, this is probably because there's online. There's a delay. And again, there's nothing I can do about that. It's very sad. Yep. There's just no getting around it. Again, the online thing is awesome, and I'm glad to offer it, but the reality is you get a better experience being in class. All right, this is better. I like this one a lot. A ball's velocity is given by 3t I hat minus 7 j hat. If the ball starts at x equals 0, what is its position vector? Is the position vector 3t I hat minus 7j hat? Is it 3 halves t squared I hat minus 7t j hat? Is it 3 halves t I hat minus 7t j hat? Or is it 3t squared I hat minus 7j hat? It may be hard to tell, but every one of these answers is different. So be careful if you're like, dude, those look the same. They are different. So just be careful. This question is seeing if you know the relationship between velocity and position. If you don't, that's okay. That's why we're all here to learn. Let's see how my responses are looking. They're looking decent. I'm pretty happy with that. All right, we'll go to 130. It's one of those, if you know what you're doing, it's quick. That's the way pretty much any clicker question I give you. If you know what's going on, it'll be a quick one to solve. 5, 4, 3, 2, 1, and close. So, how do we figure this out? Well, we remember that velocity is the derivative of position with respect to time. What's the opposite of a derivative? An integral. So if we integrate velocity and we integrate this side with respect to t, give myself a little bit more room. If I integrate my velocity with respect to time, I return my position. So if we just integrate this function, 3t I hat minus 7 j hat, remember I hat's in the x direction, j hat's in the y direction, we will get 3 over 2 t squared I hat minus 7t j hat plus a constant. Yeah.
I was going to ask, is this a closed integral?
It is not a closed integral, but we have a boundary condition. So this is a great question. There is a constant here. How do I figure out this constant? The problem says if the ball starts at x equals 0. So at time equals 0, this term goes away, this term goes away, long story short. So this should equal 0, which means c equals 0. That was purposefully chosen to make it not as gross. And most of you probably did, a lot of you may not have thought about that, but it is important. Closed integrals, the C goes away. Open integrals like this, it doesn't. You need a boundary condition. You need a value at some point to be able to determine what C is. And there you go. That's what it is. And the answer is bam, right there. And, you know, to be honest, I should have been more clear here. If the ball starts at x equals 0 and y equals 0, because actually there's a constant that goes with each one of those things. So, to be honest, I should have put that. Didn't do as good as my x, y independence. You actually didn't have technically enough information to solve this. Now you do. Anyway. Alright, let's go visit our bird. A bird flies straight 45 degrees above north. That's a weird wording. Above north. That should be above east. Above east. It says above north. Alright, I'll fix that. It should be above east. You can't be above north, because north is pointed straight up. Alright, so that should be above east. A distance of 95 kilometers for 3 hours, with the x-axis due east and the y-axis due north. What is the displacement in unit vector notation for the bird? What is the average velocity for the trip? Alright, now, I'll be honest with you all. We technically need to convert hours here to seconds. We can do that at the beginning, or we can do that at the end. I'll convert it. I'll do it now. As much as I don't want to. I'll do it now. But let's draw a picture. A bird flies 45 degrees for 3 hours. So it travels this distance. So my distance here, my R equals 95 kilometers, km. I don't really have room. I'll convert it off to the side in a second. And this angle here is going to be 45 degrees. Okay? So step 1, what's given? My R is given as 95 kilometers, which is 95 E3. Multiplying it by 1,000 to convert it to meters. We have an angle. We can put that here. Honestly, putting it as a given isn't super useful. It kind of is, but the picture, you have to know where that angle is for it to be meaningful. And the time is 3 hours. To convert that to seconds, it's 3 times 60 times 60, which ends up being 3 times 3,600, which I ain't going to try to do that in my head. 3 times 60 times 60, 60 minutes in what a wonderful number. And I'm going to use scientific notation. 10.8, you know what? Let's do it the right way. 1.08 E4 seconds. I don't know if that actually saved me much, but it's good practice for y'all. Scientific notation is useful. Okay, so the question asks, what is my displacement in vector form? So vector forms mean some number I hat plus some number j hat. And displacement is technically delta r, so we'll put that little delta r there. So we want it in vector notation, and it says what is the average velocity? V average equals question mark. Okay. All right, so again, components. Woo! So the first part, very straightforward. We're going to find, and this is where I should have made this bigger. Now it's bigger. Okay. So we're going to find the x component and the y component. That's what we have to do. So we want Rx, or we can just call that delta x. And we want delta y. That one's that way, that one's that way. Triangle. If I want the delta x, that's going to end up being my delta r times cosine of theta. If I want my delta y, that's going to be delta r times sine of theta. I did not have those memorized. I figured it out from trigonometry. X is the adjacent side, so TOA, If I want the adjacent side, it ends up being rearranged with cosine. If I want the opposite side, it gets rearranged with sine. All right, cool. Fairly straightforward, we can do that. And then at some point when we want to get average velocity, we have options. Average velocity is defined as a couple things. Honestly, actually, in this case, we kind of just have one option. It's the change in r over t. This thing went straight that way, did not go to the right, and then go up. So because we are so blessed and that we know its distance it traveled, we didn't actually have to go backwards and do all that. That'll actually be fairly simple for us, but it's good kinematics reminder. All right, so we plug in the numbers. Delta x is going to be 95 E3 cosine of 45. That'll spit us out something. Delta y is going to be 95 E3 sine of 45. That's going to spit us out something. And V average is going to be 95 E3 divided by 1.08 E4, and that'll spit us out something. It's nice to get all your stuff kind of set up, because then you can just start calculating. 95 E3 times cosine of 45, and then I'll do 95 E3 times sine of 45, and I'm just plugging them all in. What's cool here, and this should make sense hopefully, 6.671 E1234 meters. They're the same. Wow. 45-degree angles, y'all, are nice and symmetric. It's split in the middle. So if you look at our thing here, it matches. The length of this, the length of this. If you draw your picture well, your answers will match. They have the same value. You can prove that math to you. So to yourself. Again, this is kind of one of the easiest examples. It's literally number one on this problem set. So it only gets more fun from here. And we get 8.796 meters per second. Okay. Now, a couple things you always want to do. The last step to the problem is not writing the answers. The last step to any physics problem is checking if it makes sense. There are so many chances. Every time you write something, every time you hit a button on your calculator, there's a chance to make a silly mistake. So, how do you check? Does my answer make sense? Okay, this thing traveled 95 E3, that's 9.5 E3. If you know anything about triangles, the hypotenuse should always be the biggest side. So, my x component, my y component should both be smaller than delta r. Because it's a right triangle. That's how the hypotenuse should always be the biggest, delta r is the hypotenuse. 6.71 E4 is smaller than 9.5 E4. Great, so that's a great, good sign for us. Great, so both of those are fine, and the same value because the angle is 45 degrees. Our velocity, does that make sense? This takes a little bit of background knowledge, and this is where I highly recommend that you have this fun fact memorized. 23 meters per second is 60 miles per hour. 23 meters per second is 60 miles per hour. In fact, I'll just chuck that up here. You don't have to have this memorized, but if you know how fast 8.796 meters per second is, without knowing that, you're a better man or woman than I am, because I don't know what 8.796 meters per, I have no idea how fast that is. Without comparison, I know how fast 60 miles per hour is. I drive cars. They go that fast. So then all you gotta do is compare this. This is about not quite a fourth, a little bit more than a fourth, or a little bit more than a third of that. 8 goes into 24 3 times, so it's about a third of that. So it's about a little more than a third. It's a little bit over a third of 60, so it's like 22 miles per hour. Can a bird go 22 miles per hour? Yeah, it can go 22 miles per hour. That's a reasonable answer. If your bird is going 70 miles per hour, that's not realistic. If your bird is going 1 mile per hour, maybe, I don't know if they can fly going that slow. So again, this is helpful. Every physics problem, this isn't just math. The numbers mean something. The numbers actually have a physical, real-world meaning, And the beautiful thing with Physics 1 is it's all about moving objects, and you all interact with moving objects all the time. In fact, you're often a moving object. So, check your answers, y'all. Anytime you solve a problem, you should think to yourself, does it make sense? And as we introduce variables, we'll have a sense of that. Now that we've introduced acceleration for gravity as negative 9.8, you have a scale for what acceleration is. If you jump off a building, if you've jumped off anything and you felt how quickly you're falling, you have a sense of what negative 9.8 meters per second squared is as well. And a meter is that big. So, there you go as well. Meters aren't too bad to work with either. Okay, great job, us. All right, 2D acceleration. Again, it's here, but it's the same. Like, there's nothing new here. X and Y are separate. That's acceleration is the derivative of velocity with respect to time. Same stuff we covered last week. I'm just reminding you here, make certain that you separate into X and Y components. Now, instead of just saying that acceleration is the derivative of velocity with respect to time, well, velocity has an X and a Y component. Acceleration will have an X and a Y component. They're vectors. And the way we denote which one's which, we put a little X next to an A if it's the X component. We put a little Y next to the A if it's the Y component. Anytime you see a subscript, it's effectively an adjective. The Y component of velocity is Vy. Or, we've seen it when we had V naught. That was the initial velocity. So those little subscripts are just little adjectives for our variables. The more subscripts, the more adjectives. So, for good or for bad, we're going to start to see V naught Y. Two things. This is the initial velocity in the Y direction. And you know what gets real fun? What if I have more than one object? Put a 1 next to it. This is the initial velocity in the Y direction for object 1. They're just little adjectives. You got to keep track of your variables. If I got two objects moving in 2 dimensions and they speed up over time, you got to label these. If I have 2 objects and I put 2 variables like this, I have no idea which one's which. Now I've got object 1 and object 2. So, notation. It's a very important skill in physics. It's a very important skill in engineering and things like that. The notation I'm using with you all, it's pretty consistent across the board. The notation I'm specifically using is because that's what you should expect to see as engineers in the future, or physicists, or whatever STEM career you're going into. All right. A particle's acceleration is 4 I hat plus 3.1 j hat. At t equals 0, its position and velocity are 0. What are the particle's position and velocity as a function of time? And find the equation of the path of the particle. That latter skill, I'll go ahead and tell you. I am not going to test you on finding I have this here, and I really like this. But I will say I'm not going to ask a test question saying the equation of the path of the particle. That's just a good thing to keep in the back of your mind. But I still like it, so we're still going to do it. Because it's interesting. Okay, so let's do it to it, y'all. So acceleration, that's the only given. That's 4 I hat, 4.0, it's the same as 4, plus 3.1 j hat. And we got our little units there, we'll chuck them there. To be honest, this problem doesn't necessarily lend itself to the 4-step problem-solving process, but whatever. All right, so we want to find position and velocity. So we want the velocity with respect to time. We want the position with respect to time in vector notation. How do we do this? We remember the conceptual definitions. Technically it's math, but conceptual is really what it leans on. That acceleration is the derivative of velocity with respect to time. And then you can kind of have a choice here. It is the second derivative of position with respect to time. Alternatively, we can say that velocity is the derivative of position with respect to time. Whatever. Both these things say the same thing. Just how you want to kind of piece it out. So acceleration is the derivative of velocity with respect to time. Velocity is the derivative of position with respect to time. That means position is the second derivative. Or acceleration is the second derivative of position. Put them all there. kind of chew on it on your own time if you're unsure. If you got questions, come back and ask me exactly what happened here. But these two pieces here should hopefully make sense to you. Okay, so now if I'm going backwards, integrals, just like we did in that clicker question. Integrals are useful, y'all. They didn't make you learn calculus for nothing. So I teach an algebra-based course, Physics 2. And, gosh, I probably said like 10 times, I can't show you how to do this because we don't have calculus. Which for them is, kind of nice because I guess they don't have to do whatever I was going to say I was going to do. But it is so useful. They make you all take calculus for a reason. It is a tool set that you need to have. And here's some easy examples of why. You cannot understand the relationship between velocity, acceleration, and position without a derivative. At least fully understand it. Okay, so take the integral. If we want velocity, we're going to need to integrate this. 4I hat plus 3.1 j hat with respect to time. You have to know what you're integrating with respect to. These are derivatives with respect to time, so we will integrate with respect to time. Very easy integral. 4t I hat plus 3.1 t j hat. They didn't have t's, now they do. Plus a constant, but we are so blessed that this problem specifically says at t equals 0, its position and velocity are 0. So c ends up being 0, so we don't have to worry about it. Just like before. If I plug in t equals 0, this is 0, this is 0, it needs to equal 0, it equals 0, look at the c is 0. But those boundary conditions are important. All right, now we do the position. We're going to integrate what we just found. 4t I hat plus 3.1 t j hat. And that is going to equal 2t squared I hat plus, let's see if I'm going to embarrass myself, 1.55 t squared j hat. It may seem stupid, but I'm going to double check that 3.1 divided by 2 is 1.55. Good job, me. And again, the same thing. At time equals 0. At time equals 0, the position needs to be 0, so c will also be 0. If I said at time equals 0, the position is 5, c would be 5. If I said at time equals 0, the velocity was 3, 0, 0, this would have to be 3. But again, it gets more complicated because there's x and y components, so it's purposefully as simple as it can be. Yeah?
If you say like x equals 5 or y equals 5, would that be?
Yeah, so technically each of these gets its own constant. Yeah, technically they each get their own constant, kind of chalked onto them. That's a great question. I will purposefully avoid that with you all. What I need you all to understand from this is not necessarily integrating, or not necessarily the boundary condition stuff, but more so the relationship between acceleration, velocity, and position. Okay, find the equation of the path of the particle. So what this comes down to, it's kind of a nifty little thing. I have the x position with respect to time, and I have the y position with respect to time. So what I can do is I can jot over here x of t equals 2t squared, y of t equals 1.55t squared. So my position is given by this, my x component. My y component is given by 1.55t squared. How do I get an equation? The end goal when it says, again, I'm not going to test you on this, but again, it's kind of nifty. This is an algebra thing. I want y in terms of x. That's what it's asking for. Give me a function that says, I want y as a function of x. Currently, y is a function of time, which to be honest,